Welcome to this Landwise presentation on soil and irrigation for irrigation operators and crop managers. One of the key components when we're talking about irrigation scheduling is understanding soil and water. Soil is made up of 50% solids and 50% holes. Those holes should contain 50% air and 50% water. Those holes in our soil are called macropores and micropores. Macropores are our large drainage holes, and micropores are our small holes that hold water against the pull of gravity and store that water in our soil. Heavy soils have many micropores, so hold water really well, and they have very few macropores, so we don't get very good drainage. Well-structured loams should have about 50% macropores and 50% micropores, so we have a really good growing medium. Our plant roots aren't rotting away and getting stressed, and they've got access to plenty of water. Light and stony soils have many macropores, so drain really well, and very few micropores, so they can't hold the water very well against gravity, and it drains away. Let's talk about some soil water terminology. So for this exercise, I want you to picture a sponge. We've put our sponge in a bucket of water, we've squashed it really tight and all the air bubbles have come out of it, and then we're going to lift that sponge out of the bucket, and as soon as we lift that sponge out of the bucket, we start to see water falling back out. That water falling out is our drainage. That's our macropores emptying out. As that empties out, we're taking our soil from saturation point down to field capacity. So field capacity is where the drainage stops and our water is sitting in our micropores being held against gravity. From there, we are going to give our sponge a gentle squeeze and water is going to keep coming out. So that's our plant easily taking out water. As we do that, it does start to get harder. And we reach a point which we call stress point, which is sort of the midway point between field capacity and wilting point. So we can still get water out of the sponge, but we're starting to have to really give it a tight squeeze. And that's our plants just taking water for sheer survival. They're no longer putting effort into growing leaves or producing yield. They're literally just staying alive. So we keep squeezing that sponge and we reach a point where water is so tightly bound in that sponge we can't actually get any more water out. That's our soil's wilting point. So our plants can't get any water out of that soil either, and so they will start to fall over and they're going to start to die. That doesn't mean that our soil is completely dry. We have another term which we call oven dry, and so an oven dry soil has got no water in it. So if you think of it in our sponge context, if you leave a kitchen sponge on a kitchen bench, don't use it for a day or two in the middle of summer and you look at it again and it's gone from maybe a darker yellow to a light yellow and the edges are starting to curl up. That's our oven dry point. We want to keep our plants between field capacity and stress point because that's where our readily available water is. That's the water that the plant can use to grow, to do all the create sugars, to improve its yield, etc. Available soil water is the amount of rain or irrigation water the soil can hold between field capacity and wilting point. It's described as a percentage or as millimetres of water per 100 millimetres of soil. We also need to factor in our root depth because a plant of a root depth of 300 millimetres has half the amount of water of a plant that has a root depth system of 600 millimetres. Let's work this through with a maths example. Our crop has a rooting depth of 400 millimetres and an available water of 20%. So 20% of 400 millimetres is 80 millimetres. But only half of that available water is actually readily available water, so 40 millimetres. Beyond that 40 millimetres, we've reached the stress point and we're starting to work towards wilting point. It's really important that we schedule our irrigation to make sure we apply water before we've used that 40 millimetres to ensure that the plants do not enter stress. Over the next couple of slides, we're just going to talk about how water moves through soil. So we have our wetting front and water moves down through the profile as each part of it reaches field capacity. So of course we've talked about macropores and micropores before, but our gravitational water moves through the macropores, so that's largely our drainage. And capillary water moves through the micropores. So capillary water, as we've said previously, can be held up against gravity. But as those pores fill up, they move on down and fill up the next horizons and layers of soil. However, soils often have what we call preferential flow paths. So if we apply water too fast, we get surface runoff, and as it runs off, it might find a crack and it will pour down through that crack and disappear. The other type of preferential flow path is where water finds wormholes and it follows down those wormholes and disappears out. Preferential flow paths are a major contributor to leaching. This is why looking after our soils and having a good quality structure that doesn't have too many macropores or cracks and holes in it allows for that water to find micropores and be held in that soil, available for the plants instead. Irrigation is not uniform. It'll never be perfect. However, we should try our best to get it as uniform as possible. Now, soils aren't uniform either, but we can't control them as easily, but we can make sure our system is functioning well. So if we look at this animation, it assumes that on the left-hand side we have a slightly higher application rate coming out of our irrigator than on the right-hand side. And so as we apply our water, we have this wetting front coming through, and on the left-hand side you can see the little drips. That's signifying an over-application, which is an inefficient use of water, and as it drips out the bottom there, it takes our nutrients away with it and entering into groundwater. On the right-hand side, we're going to claim that it hasn't actually reached the full rooting depth, and so those areas where the roots are still dry, they're not getting the water that they need. That is ineffective irrigation.